Good evening. I suppose I should explain my main motivation for being here tonight. Apart from the pleasure of seeing my good friend Andrew Lyon, you see here I'm at Birmingham University. Of course, this is a lie. I was at Birmingham University, but I've now moved to Spain. And what happens in Spain, of course, is it gets very hot and very sunny, and you're always looking for opportunities to cool off. So where better to cool off than in Glasgow? That's my second motivation for being here. That's the one I don't tell people about. But anyway, I'm really pleased to be here, and we'll talk about this work at CERN. As Carol pointed out, CERN and the Atlas experiment is a rather strange beast, okay? Essentially, what I will explain a little bit about what the experiment is, and then I want to talk about the organization using a conceptual framework, which I've been playing around with for too many years to remember, frankly. But it's essentially, I'm going to be looking at the construction of a detector. This is a machine that detects collisions and the tracks of particles that are accelerated to 9.9999% of the speed of light. I hasten to add, I'm not a physicist. I nod a lot and I smile a lot when I'm interviewing physicists, and I go, yes, yes, and they all think I know what they're talking about. And the answer is, well, you know, I pick up the odd word and then I put it in, I record it, I try and make sense of it. But essentially, it is one of 4 experiments that straddles the Large Hadron Collider, which is this 27-kilometer tunnel. I'll talk about that in a second. The accelerator has pushed particles to the highest levels of energy ever recorded on Earth. So we're talking about completely new stuff, new physical phenomena, okay? The detector is gigantic. I'll talk about that. And as Carol said, it's actually 3,000, because it's a moving feast. It's, when I started work with them, it was 2,500. Now it's gone up to 3. It was 138 institutes. It's now 174. So it's a movable feast, and it's a network. And it is a very, very complex process. So one of the things we're interested in is how is coordination achieved in such a complex organization? And is there something we can learn about this in other kinds of complex organizations? So you can think of cities in many ways as having the kind of complexity that you see there. And so it is an open question. I'm not going to prejudge whether you can. You're going to have to be the judges of this. I will present what I see in my work at CERN, and then we can explore, well, is there something here that can be transposed and is relevant to the kind of problems and challenges one faces in a city like Glasgow? Okay, so this is the Large Hadron Collider. Now, I want to assure you that when you fly over the city of Geneva, you do not see this tunnel. Okay, this is actually buried 300 feet underground. You're at the bottom of a 30-story building, and part of this goes under the Jura Mountains in France. Over here, you can just see the runway of Geneva Airport. So it gives you an idea of the size of this thing. So this is 27 kilometers in circumference. There were movements detected in this tunnel of about 1 millimeter, and these were due to the gravity effects of the moon, gravity pull of the moon. So it would vary by 1 millimeter, and they concluded this was lunar action. I just want to explain what happens, that particles, this is what you've just seen. This is an aerial view, right? And you've got 4 detectors. There's one called Atlas, one called CMS, which stands for Compact Muon Solenoid, one called LHCb, and one called ALICE. 4 detectors, and the reason you've got 4 is in science you have to replicate your experiments, because if you don't replicate, you can't prove the phenomena you're looking at. The problem is you can't go somewhere else and say, oh, let's build another 27-kilometer tunnel, because this tunnel costs $6 billion to build. So essentially, replication has to be done on the same machine. So you're going to use 4 different kinds of technologies, and you're going to see if one of them detects something called the Higgs boson, the others are going to try and replicate it and see whether they see it using a different technology, and that counts for replication. This is the machine. This is what a detector looks like. If you want to get a sense of its size, here are a couple of people standing just over the tunnel itself. So this machine sits 30 floors underground, weighs as much as the Eiffel Tower, has 15 million parts, and is the most complex piece of technology ever built, which is why it's interesting. So I've been working with the project manager of this, and I've been interested in how they are organized and what comes out of it. And so we're looking at, well, how do they produce knowledge? What kind of knowledge? What can we do with it? This is the organization. Just very briefly, this is what we call the governance side. So there is a collaboration board, a resource view board that looks at the money, and there's a kind of plenary meeting of the 3,000 physicists. Here you have somebody called a spokesperson. If this was a commercial company, that would be called a project manager. The reason he's called a spokesperson is that although he's responsible for this show, he has no managerial authority. I say he, this is an exaggeration. Today it's a she. It is a woman physicist who runs this, supported by a technical coordinator, a resource coordinator. Now, why is it that these people have no managerial authority? It's very simple. Down here you have the different research teams that are each responsible for one component of this detector. So you have, for example, a tile calorimeter, which detects the heat generated by a particle when it goes through a particular kind of material. Then you have something called TriggerDAC, which is about how do I register the data from a collision. And you get about 1 billion collisions a second, and you're going to have to analyze those. You're going to have to analyze the trajectories using 20,000 computers that are sitting down in the tunnel next to the machine. And you're going to have to do that in 1 second. And then you're going to have to take 200 of the most interesting one of these collisions and farm them out to these 174 institutes. So this is quite a lot of work. These people are employed by their institutes. They're not employed by CERN. They're not employed by the Atlas collaboration. The collaboration is held together by a memorandum of association, not a contract. So here's the problem. I'll come on to this. I'll be jumping in and out of slides. So the question is, how does a situation like this, where this spokesperson cannot give orders, manage to coordinate something as complex as this piece of machinery? This is an astonishing performance. And they've done it. So it's something which exists. It's not just an idea. And I want to just show you what the problems are looking at a performance spider graph. So a performance spider graph says, at the very center here is zero performance. This is zero performance. Out here is performance such as we've never done it before. So that's the tip of your spider graph. And then you can look and say, well, where are we trying to achieve performance? If you're outside that envelope, you're really in a territory which nobody's been to before. If you're inside this dotted line, other people can do this. So you can see you're stretching. You think of a piece of elastic, and this thing is going out and it's stretching, which means as I increase the collision rate, I've got an increased problem of detecting particles. So you can see there's an interaction. As I have an increased problem in detecting particles, I have an increased problem in data acquisition, registering and analyzing the data. So these things interact, and they interact in ways that they've never interacted before. So you're pulling this, imagine this is an elastic, you're pulling it taut, and the more you're pulling along these new dimensions, the more these interactions are going to take place in ways that you can't control. The looser, the closer you are to the origin, to the center here, the easier and the more manageable it gets, because you can separate these performance dimensions and you can manage them on their own. So you see, we're not just dealing with high levels of performance, we're dealing with a machine where everything interacts with everything else. So you're dealing with a highly complex interactive system, very much like a city, which is why I think there might be some interest. So just to summarize so far, the collaboration is held together by memoranda of association. Most of the decisions are bottom-up, and it's a fascinating process because it's all meetings upon meetings where they actually constantly, each group is presenting to another. So the coordination is done by groups interacting virtually or face-to-face. And the managers only intervene very, very rarely to encourage, to motivate, but very little else. So how do you manage to reach the tip of the performance spider graph? And what implications for the way we run our businesses? Is there something to learn from this? I could go on about this because they've had management consultants in saying, we're going to teach you about management. And the management consultants say, they come out of this after 2 years saying, actually, we're the ones that have something to learn. It's a modesty generating machine, if you like. especially for management consultants. So now I want to just look at the framework that I'm using to look at this. And it's quite a simple framework. I'm embarrassed to have spent so much time developing it because people look at it and say, it's that simple. What have you been doing with the rest of your time? Well, anyway. Three kinds of knowledge we can have. There's the kind of knowledge which is experiential. This is what you get through your senses. I see you sitting here, you see me talking here. It's direct, okay? It's intuitive. We don't have any problems with it. Then there's a small part of this knowledge that we can articulate and we can transmit verbally. So you don't have to be present in the experience. You can actually convey it verbally. And the limits of that knowledge are the limits of how far my voice can carry. Okay? So you can use it on the telephone. You can still get quite a lot of experiential stuff, tone, pitch, all sorts of things. You can get emotions. But only a small part of this knowledge ever gets translated into abstract symbolic representations, things that you put down on paper, where you're using symbols, you're using script, you're using numbers. So you've got a kind of filtering process that says the closer you are to the here and now, the closer you are to this. And then you gradually, your knowledge becomes sparser as you move towards the abstract symbolic end, towards these very sparse representations. You can put this on a scale, and this is what I've done here. And down here, you've got the very experiential stuff, and little by little, you can compress it into codes, which you can then use and articulate verbally. You can convert it, you can compress it further into abstract symbolic knowledge. Of course, as you do so, you begin to lose some of the context, and we'll talk about that because this is an important issue. Here's the key idea behind the framework, that if I put a population, and a population of agents, agents could be the people in this room. Agents could be the population of employees in a firm. Agents could be a population of firms, which means I'm now looking at an industry, or I'm looking at a strategic alliance, or I'm looking at a network of some kind. And in a given unit of time, this is as far as I can get in terms of transmitting experiential knowledge. You know, it wouldn't get beyond this room because there are physical barriers to the kind of direct experience of Max Boisot speaking. Well, with narrative knowledge, I can get somewhat further in the same unit of time. And with the abstract symbolic stuff, I can actually maybe reach the whole population. Think of a stock market, and this is actually the next slide if I remember rightly, yes. Think of this knowledge down here as the knowledge that the Zen master has, where your disciples are sitting at his feet, and you might spend 2 or 3 years with the same master trying to pick up by osmosis what the message is. And it's ambiguous, and you need trust, and it's transmitted face to face. There's no other way. He doesn't hand you a book and say, this is my writing, go off and study it. That's not how you pick up Zen mastery. At the other extreme, you've got bond traders who are spread all over the world. They only deal with quantities and prices. They have some distrust of this kind of intuitive kind of knowledge. They want stuff that's been tested, that's been codified, that's been stabilized, that's been conventionalized. And this kind of knowledge diffuses instantaneously. You just push a key, and the day, that stuff diffuses instantaneously. So 2 completely different kinds of knowledge. We tend to think of scientific knowledge as this. I'm going to suggest to you that the really interesting stuff is down here. And the big problem is, well, how do you relate them to each other, and what does that mean? There's another point. I don't want to spend too much time on this, but what happens is, if you want to extract value from your knowledge, and this is particularly of concern to commercial firms, you're going to have to push it up here because the utility of knowledge increases as you can manipulate it, okay? If you want it to be valuable in a commercial sense, you've got to keep it scarce. So here's a paradox that a lot of knowledge is valuable when it occupies this region because it's scarce and it's useful, but it's also the region that is where knowledge is at its most diffusible. That is, in the information economy, the most valuable commodity is actually unstable with respect to value. If I take a physical object like this jacket doesn't replicate, but knowledge replicates instantaneously with a photocopy. So the basic problem with knowledge is that because I can replicate it so quickly, it may take me, I could spend £1 billion coming up with a new formulation in pharmaceuticals. But it'll cost me a penny to replicate that and diffuse it. So you can see the paradox that actually this is not a stable region, whereas with a physical good, that tends to be a stable region. And so a lot of behaviors to do with how people use knowledge and how they behave with it is to do with that instability. Well, there are a lot of reasons why we like to codify knowledge, because you can manipulate it, you can treat it like an object, you can store it, you can write contracts. There are all sorts of things, and of course you can buy and sell it. But as I said earlier, you lose context, you lose richness. And this is my favorite slide. Anybody know what this is? It's Hurricane Katrina gathering its skirts over New Orleans. And what I always invite the audience to do is to think, okay, you're driving down this road, right? You can just see a road here. You're in a car. You're beginning to get these raindrops the size of ostrich eggs falling on your windscreen, going plof, plof. The wind is beginning to roar. Your car is being pushed off the road, right? You're getting into this. So you take out your cell phone. You send a text message to Mummy. Mummy, I'm driving through a hurricane. So the question is, how much of your knowledge of the hurricane do you think you've just transmitted? That is the loss of context. That's what we're talking about, okay? So essentially, there is going to be a large part of what you know that is not articulable in any conventional sense. Where does it come from? What are the implications? Well, I want to switch. So having given you the basic framework, here's one thing you can do with it. You can say that knowledge moves through interactions with people, right? Whether you're communicating with a bond trader or whether you're communicating with a Zen master, you're in some kind of interaction. And there are different ways. These interactions give rise over time to structures. If the interactions are recurrent, you can build structures, institutional structures, cultural structures to capture them. And as Andrew well knows, as an anthropologist, you know, culture is about the way you articulate things in the world and who you share them with. There are street corner cultures, which are basically small groups that interact on a regular basis. And then you've got nation states, where you've got large groups that interact with each other at random on a much larger scale. So just to give you an example, a market culture is built on a certain kind of information. Market price. Market price assumes that information, everything can be codified into the price, and all that knowledge is available to everybody. So an efficient market, it's a theoretical construct, but an efficient market is an institution or is a market in which all the relevant codified information is diffused instantaneously. Okay, that's one kind of culture. We look at bureaucracy. Well, we see that it's also pretty codified, and bureaucracies write things down, they write records, everything is put down on paper. But now, the diffusion is under some central control. Bureaucracies operate on a needs-to-know basis. So markets operate on the basis of transparency, bureaucracy's instinct. And of course, I am aware that there are plenty of efforts to make bureaucracies move further in that direction, but that's not the instinct. The instinct is control of the flows of information. An organizational chart is just a map telling you who gets what, under what circumstances. So if you come down the space, you notice that curve says, well, actually, this is not something to which information diffuses instantaneously because it's viscous. You're further down the space. This is much less codified. It's much more concrete. So what happens is, per unit of time, only a small group is likely to get access to that information. What happens? Well, the first point to make is that group is much more likely to be interacting face-to-face with people who know each other and share values than a market. That's the first point. The second point is that having that information is what distinguishes a clan from the outsiders. So clans have in-groups and out-groups. And very often the in-group will solve its problems at the expense of the out-group. So again, very, very different value system. Clans depend on shared experiences. Professions have shared training. Different combat units will have had a shared battle experience. If you've been to the same school, you will belong to an alumni group. So there are plenty of examples of what we mean by clans. And we can see that whereas in a market nobody needs to know each other, you don't need to know the bond trader who's just bought your bond issue. In a clan, are you one of us, is the first question that's being asked. Okay, this looks very strange. What is it? Well, down here, we've got the kind of knowledge that is almost impossible to articulate. It's very often unique. It's a source of what you would call charismatic power. A Nobel Prize winner might have the kind of insights and the kind of knowledge here that give you that power. Maybe there are skills that you can't articulate, because if you could articulate them, then you'd start sharing them. So essentially, a fief, historically, is a space over which you have some kind of power, personal power or jurisdiction. So, we talk about bureaucratic fiefdoms when, over time, the kind of knowledge you've acquired here gradually gets internalized and gives you that kind of unique knowledge of a particular part of the organization. And you can actually exploit it very often for personal ends. So fiefs are actually not necessarily negative or positive, but they are spaces over which you have personal power. That's all it really means. So I want to use this now to think a little bit about how Atlas functions. The first point to make is that the kind of information environment that you get in different parts of this space have very different properties. For example, bureaucracies are permanently in quest of order, stability, and predictability. As you move away from that diagonally, things become more complex. That is to say, they become more complex partly because you're increasing the number of players and because the information you're dealing with becomes fuzzier. So these two things together, you get more cognitive complexity and you get more what we'll call relational complexity, because with people sharing it, you've got to be able to interact. A larger group is interacting here than here. Inside a bureaucracy, your reporting relationships are quite structured. So you don't want to look at the bureaucracy as a whole. You want to look at the span of control and say, okay, I can keep a control over who I interact with and how. As you increase the numbers that are in interaction, the complexity goes up. And then as you move and incorporate ever more of the population, and as your cognitive complexity increases, you're now in an area here which I'm using the term chaos, not in the sense of a mess. I'm using the term chaos in the sense that you cannot extract any meaningful structure from the interactions you're looking at. So this is chaotic in the sense that actually you may not know what's going on. It may be very difficult to understand it. So, there's an expression in complexity theory called the edge of chaos. And you can see that clans are very often quite unstable because they're very close to this area. So if you like, bureaucracy, there's a constant flight towards order. As Carol mentioned, I spent 5 years in China working in the economics ministry. And the one thing that you realize is that a lot of the regime's political philosophy is driven by a total terror of finding itself down here. And the quest for order verges on the pathological. I mean, this is in the political system. So it's a kind of interesting idea. The Chinese view of the world, their cosmology is there is chaos and there is order. There is no concept of complexity as some mediating form of institutional arrangement. I want to now just move to another point which is relevant to our story. What happens when you introduce information and communication technologies into the picture? Well, this is pretty important to CERN's story because, of course, as I mentioned to you, there are 20,000 computers sitting down in that tunnel. And there's a massive, when you bear in mind that it was CERN that gave us the World Wide Web in 1991. They built on the internet, what was then the Ethernet, and they built a system that delivered the World Wide Web. So information technology is a very big part of the picture. It's almost half of the value of these experiments is their ability to make use of computers. So here's one way you can look at it. You can say, at any level of codification, the whole of that curve shifts to the right. Why? Because you've got something called a diffusion effect that says, in a given unit of time, I could only reach this number of people with this technology. With information technology, I can now reach that number of people. So it's just a rightward shift in the curve. But now look at this second effect. In a given for a given size of population, I can now reach these people at this level of codification as opposed to that level of codification, moving from here to here. What does that mean? It means, and I had direct experience of this when the fax was introduced in China. When I was working in China, we used to go and send telexes. There were about 5 telexes that foreigners could use in Beijing in 1983. So you get in a line behind other people who want to use the fax, other foreigners. And you've got a non-English speaking Chinese girl who's actually very competent at typing, but doesn't speak any English. So she's going to type up your message. What happens? Well, there's a 50% error rate. So you get your message back, you say no, you go back to the back of the queue, you try again. When you try again, your message is shorter. Again, 50% error rate, so you compress your message again. So what are you doing? You're constantly moving your message up here in order to avoid the errors. Along comes the fax. No telex operator, I handwrite. And the thing was that with the telex, all my messages were to the European Union, who was running the program that I was in charge of. And so your messages are quite short, terse, and pretty impersonal. Within a year of the fax, we were doodling, sending little cartoons, cracking jokes. The whole thing had got personalized. And that was the fax. Look at what you can do with video conferencing. Look what you can do with the internet today. So my point is, you're exploiting what's called the bandwidth effect. So here's an interesting story. What starts off as impersonal communication now gets personalized for the same cost. And that also is an important part of what's happening at CERN. So if we want to link this to our story of the different institutions, what you see is that the diffusion effect would move you further from markets, the bandwidth effect would move you closer to clans, and both of them are moving you away from bureaucracies. So this is one of the impacts of information technology. It actually increases the cost of maintaining control. As you can see, if you look at the news on how difficult the Iranian authorities are finding it to control people who are using cell phones to tell outsiders what's going on, they've lost control of the flow of information. And some of it will go that way, and some of it will go this way. So now we can use this framework to start thinking about okay, so I'll skip that one because we've said it. Now we can look at what's happening to Atlas. Atlas is 3,000 people, highly scattered. I would argue that they are actually beyond clans in terms of the size, and that they represent what an organizational specialist called Henry Mintzberg calls an adhocracy. So an adhocracy is a kind of loose network that organizes and self-organizes. And the question is, well, how can anything here, given that we've put it to the right of clans, and you know, it's very much built on the norms and values of the scientific community. So it has clan-like qualities. You know, the whole collaboration is built around the idea that we have shared objectives, shared values, but we do not have bureaucratic control systems, or they're rather light. They are there, but they're very light compared to what you'd find in a conventional commercial organization. So the question is, well, what stops this from flying apart? I mean, if it's down here, and given that you can't get structure, what is it that keeps it together? What's the binding agent? And this is the hypothesis that we're now working on. So here's just a few pictures to get you thinking about what we mean by control. So in a traffic light, you've got an object. That represents authority, right? You know that, you feel it. You know, you see a red light coming on, you go, whoo, and you put your brakes on. It's automatic, it's instinctive, okay? The problem with those systems is that it can get a bit confusing as the organization grows, okay? So, you know, it wouldn't be too clear how you would react to a traffic light that you came across that looked like this. Well, put it this way, if it is clear, come and see me after the talk. I'd love to talk to you, okay? So this is another kind of, the kind of problem that you have with hierarchical control. There are situations that just get too complex to be represented in simple ways. So, are there other ways of getting coordination? Well, of course there are. What about this? A roundabout. There is still an authority. I mean, there's a rule, you know, give way to the right, etc. But essentially, that will cope with anybody who's been to Paris to the Place de l'Étoile will realize what looks chaotic to a pedestrian. By the way, don't try and cross as a pedestrian at the Place de l'Étoile in Paris, right? But essentially, there are some very simple minor rules, and the whole thing is self-regulating. So we call this a boundary object. It's a physical object that actually helps a coordination that under other circumstances would be regulated hierarchically. And this massively simplifies the process of coordination. And I live in Spain, and one of the things I've noticed in the last 15 years is a massive increase in the number of roundabouts that you see. So that, to my mind, is actually a signal that the country is becoming a little less authoritarian. You know, Franco died in 75, and it's only now we're beginning to see the boundary objects becoming a little bit more democratic, away from traffic lights and towards roundabouts, okay? And so the suggestion is, okay, the reason you can handle the chaos is that this is actually a collection of boundary objects. I talked about these teams constantly coordinating and interacting with each other. What makes those interactions meaningful is that they're all able to focus. They have a common understanding of what a tile calorimeter is, what a liquid argon calorimeter is, etc., etc. So the object itself begins to generate its own coordination. The Atlas experiment started in 1984 as a very rough set of simulations on a computer. Then those simulations became more detailed, and then they increased the number of variables and parameters. And then the thing got ever more complex. And at a certain point, you began to introduce physical objects instead of simulated objects. So now you had a mixture of simulations and physical objects. And little by little, this physical object emerges from all these sequences of simulations. And so here are the different teams, and they relate to each other, and they relate to the object, and the object creates a shared understanding, a common language, a common understanding between them. And so, in a way, the object acts as a substitute for a coordinating bureaucracy. It is an object that we have here. It is no longer a human hierarchy. And so you can think of this as a kind of magnetic field where the adhocracy remains in the orbit around the object, and the object organizes the adhocracy. Now, I hasten to add, this is a hypothesis that we're working on. It's not something you can prove. This is a way of thinking about what's going on. What is interesting to me is that it's very plausible to the players themselves. I mean, I tried out with the project managers, the people running the things. Yes, we think this is how it works. So we're still playing around with this, but this is where we're at in our research. Okay? I've got a proposal out that I'm hoping we'll get funding for, we're waiting to hear, comparing NASA with CERN, a NASA project with the CERN project, with the Atlas detector. This is interesting because NASA is essentially run by engineers, and the scientists are in tow. So the kind of, what engineers do is they use whatever knowledge they've got in the most efficient way possible. So you're trying to deliver efficiency. One of the problems that you have with this is that sometimes it means that you want to move up towards greater levels of codification and abstraction much faster than your understanding allows. In other words, you're efficiency driven. There are many people who've studied the Challenger disaster of 1986 and the Columbia disaster 10 years later, and who believe that actually the urge to codify and structure prematurely was a large part of the explanation of why those accidents happened. If you look at CERN and Atlas, you're dealing with an ecology. You're not dealing with a matrix structure where you basically had the technical access. These were the experts. Here were the project managers who were responsible for price and performance and time. So this was a conventional authority-driven system, looser than a conventional hierarchy, but still an authority-driven system. This is a bottom-up, self-regulating process. Again, using a mixture of boundary objects, very light levels of authority. But that's a very fundamental difference. And so the question, in a way, okay, the questions, I mean, this is the hypothesis. Let me come to this first. So the Atlas collaboration is navigating multiple stakeholder cultures because you've got 20 members of CERN, member countries, and you've got many, many more who are participating in the actual collaboration. And they're operating under different mental models, different models of what their loyalties are. So you're really dealing with a complex cultural ecology. And as I said before, essentially trust and shared values seem to be the binding agent that are allowing this level of complexity to occur. Okay? So essentially, I'm arguing that the detector acts as a boundary object that binds a cultural ecology into a complex adaptive system. So just to finish up, I'm going to skip this because I think it's going to take us away from what I want to say. You can look at a city like Glasgow as a complex adaptive system. The edge of chaos does not mean chaotic. It means it's perched on the edge of chaos. In other words, there is a thing in complexity theory called self-organized criticality, which says, actually, at the edge of chaos, you get a certain amount of self-organization. I'm not going to go into how that happens or why it happens. I don't think we actually understand it too well. But essentially, I would argue that a city also provides a collection of boundary objects. And then the question is, well, what are the self-organizing possibilities of these collection of boundary objects? I've become aware through my discussions with Andrew of something called the Glasgow effect, okay? And my hunch, and it is up for discussion, is that it might be interesting to see to what extent there are available resources in the forms of boundary objects in any urban environment, and Andrew would call those urban assets, I think would be the term he would use, that might actually help to address the problem. In other words, instead of framing the Glasgow effect as a problem that we have to coordinate and we have to manage in a conventional way, are there ways of dividing up the labor with objects in our environment that will take some of the load for us? And I think, I mean, in a way, much technology has the same quality. Much technology is a form of scaffolding that allows us to do things that we want to do. Well, I don't want to use the term technology because it sounds too techy. I just think that a city is a physical collection of objects that has many of these properties. You know, the thing is that some of these are tremendously self-organizing. I mean, you can think of vernacular architecture as an implicit understanding of the rules by which the city keeps generating itself. So there are going to be ways of thinking about this that I'm deeply interested in because my original training was as an architect and as a planner before I got involved in this weird kind of stuff. And so I am actually interested in exploring this. And that's pretty much it. I think I'm leaving it with the questions open for discussion. Thank you.